Welcome, listener, to another deep dive.
Hello.
Today we're plunging into a topic that literally redefines reality: quantum physics.
hmm
It sounds incredibly complex, I know, but we're going to unpack its profound impact on everything from, the device in your hand to the future of medicine and cybersecurity.
That's right. We're going to explore how a series of, unexpected cracks in our classical understanding of the universe led to this revolutionary new science.
Right.
Our mission is really to extract the most important nuggets and surprising facts from the sources you've provided. Make the truly weird incredibly clear, hopefully.
Let's make it clear. So let's jump in.
Oh.
When we think of classical physics, we usually think of Isaac Newton's world. A universe of certainty, predictability.
Clockwork universe, sort of.
Exactly, where everything moved along definite paths. But then some strange phenomena started showing up, like the ultraviolet catastrophe,
Yes.
which predicted absurd amounts of energy radiating from hot objects. It just didn't make sense. It was as if the universe had a secret.
It really did. And what's fascinating here is how Max Planck and then Albert Einstein brilliantly resolved this.
Yeah.
They proposed quantum
We disagree.
indivisible packets of energy. This was a radical, almost heretical break from the past.
A huge break.
It revealed a universe that's granular, not smooth, and fundamentally probabilistic at its core.
Hold on, fundamentally probabilistic, that really shatters our everyday intuition.
It does.
So if the universe at its core isn't fixed, does that mean our classical sense of certainty was just...
Well, an illusion.
Pretty much. It forced a complete rethinking. Think of it this way. It's not just that we don't know the future, it's that the future itself isn't fixed until it, happens at the quantum level.
Wow.
It's like the universe is playing dice, as Einstein famously disliked admitting.
God does not play dice.
Exactly. But it seems it does. And that very strangeness leads us to the core ideas that make quantum mechanics so mind-bending.
Okay, here's where it gets really interesting. First, superposition.
Imagine a quantum bit, a qubit. It's not just a 0 or a 1, but both at the same time.
Simultaneously.
It's not like we just don't know which one it is, like a
Right.
hidden coin flip. No, it's a genuine state of coexisting possibilities. Until you measure it.
Precisely. It's a fundamental difference. It's wild to think about.
It really is.
And then there's entanglement. This is what Einstein famously called spooky action at a distance.
Spooky action. I love the phrase.
It's perfect, isn't it? Two or more particles become inextricably linked. So measuring one instantly influences the other, no matter the distance.
Instantly, across space.
Instantly influences its state, yeah.
Yeah.
They behave as a single, unified system. It's as if they're communicating faster than light, though. Importantly, no information is actually traveling faster than light. It's correlation.
That's incredible. So we went from these, theoretical packets of energy and these mind-bending concepts to literally building our modern world. How did those abstract ideas leap into something as tangible as, say, a smartphone?
Well, if we connect this to the bigger picture, these strange rules weren't just abstract ideas. They power the very devices you use every day.
Right.
This is what we often call the first quantum revolution, basically. Understanding and then manipulating these quantum phenomena in material.
Your smartphone is the perfect example, right?
Absolutely. Its digital heart, the transistor, is a purely quantum-engineered device.
Okay.
Understanding the electron's quantum behavior in semiconductors through concepts like energy bands, think of them as specific, allowed energy levels for electrons.
Like lanes on a highway?
Sort of, yeah. And doping, which is like carefully adding impurities to fine-tune those levels.
Yeah.
That allowed us to control conductivity precisely.
And that's how we miniaturized electronics. From huge vacuum tubes to these tiny microchips.
Exactly. It all rests on quantum mechanics. Now, we're entering what people call a second quantum revolution,
Okay.
where we're directly harnessing the really weird stuff. Superposition and entanglement.
And this is where quantum computing comes in.
That's the most famous example, yes. Instead of classical bits, zeros and ones, quantum computers use qubits.
Which can be 0 and 1 at the same time.
Right. Leveraging superposition and entanglement to represent potentially all possible solutions simultaneously. This allows for vastly more powerful computation, for certain problems anyway.
Tasks that classical computers just can't handle.
Can't even dream of in some cases.
And the applications are truly mind-blowing. You hear about revolutionary drug discovery.
Simulating molecules to design new medicines, yeah. Or creating novel materials atom by atom. It's like having a universal simulator at your fingertips.
But there are hurdles, right? It's not easy.
Oh, absolutely. The major hurdle is decoherence. Quantum states are incredibly fragile.
Fragile.
Yeah, they lose their quantum properties very easily due to interaction with the environment. So you need extreme cold isolation. That's a huge engineering challenge.
Got it.
But beyond computing, this revolution extends to quantum sensing, promising ultra-precise measurements.
Like for medical imaging. Or maybe navigation without GPS.
Yeah.
Exactly, those kinds of things. And quantum communications, aiming for inherently unhackable information sharing.
Unhackable. That sounds crucial. Which brings up a big question. What does this mean for our world right now? The most immediate impact seems to be on cybersecurity.
Definitely. A powerful quantum computer, once built at scale, could break most of the encryption that protects our online banking, our communications, government secrets, everything.
That's terrifying. It's this harvest now, decrypt later vulnerability people talk about.
That's the worry. Data could be stolen now, stored, and then decrypted years down the line once the quantum computers are ready.
So what's being done?
Well, the response is a global race, really, for quantum-safe solutions.
Okay.
That includes new mathematical algorithms, what's called post-quantum cryptography, or PQC, and also physically secure methods like quantum key distribution, QKD. It's a fascinating race against time.
So, wrapping this up, what does this all mean for you listening? The quantum world is profoundly weird, no doubt about it.
But its rules are the foundational bedrock of our modern world. And they hold the key, potentially, to solving some of humanity's greatest challenges.
It really pushes the boundaries of our understanding. And there are still deep mysteries, like the measurement problem.
Right. What actually happens in that moment when a quantum system's multiple possibilities collapse into a single reality just because we observed it?
We still don't have a universally agreed upon answer. What exactly is happening there? What constitutes a measurement?
It reminds us that in the quantum world, the observer isn't just some detached spectator.
No, you're an active participant.
Which leaves us with a final thought to mull over. What part do you play in shaping the reality you observe every day?
It's fun to think about.